Hello everyone, I'm Ben. I'm going to use this simple type for my examples. It's pretty boring. I've got two colors, red and blue. And in Haskell we can write these wonderful pure functions that convert bools to colors, like case to color, true goes to red, false goes to blue. But then we get into these awkward situations where we want to perform effects. So suppose our Boolean is actually in a reference and we need to read the reference to do the case expression. Now we know in Camel, in SML, they use implicit effects. The program is equally convenient to write as the pure version, but because they have implicit effects, they lose track of this. You can't do fusion, the program's harder to reason about, laziness stops working. So this is no good. So in Haskell, we use I/O for effects, but then we have a type which tracks the fact that we're using effects, but we can't write the same code. So the type is what we want, but the code doesn't work anymore. So we end up writing things like this. So we use do notation. We read the reference, we do a case expression on the resulting value, and then we can return the final result. Now, this has been annoying me for 10 or 12 years now, and I'm sure it annoys some of you as well. So it's even like doing this simple transformation, like from there to there, isn't too bad because you just have to move the scrutiny up a line and write do. It's not so bad. But there are other situations where you want to use, say, pattern alternatives. Imagine you have a long list of pattern alternatives and you have a color C there, and then you want to write a new version of this function which changes the color to a reference to a color. And then now what do? You have to rewrite the whole thing, okay? Because pattern alternatives supply a very useful notion of control flow which cannot be captured in our standard do notation. So we're forced to rewrite reams of code when doing this sort of thing. So I'll show you a better way to do this. So we take the function that we were trying to write, and I'm going to introduce two new keywords, run and box. Okay, these are keywords in the language. You can imagine them as typecasts. So what does run and box do? Okay, I'm also going to introduce a new type for readref. So whereas the Haskell version of readref or readiref returns an IOA, my readref returns a sReadA. So S is a indexed computation constructor. You can imagine S means state or S means suspension. Either one's fine. Read is the name of the effect and A is the return type. So the highlighted expression has the type sRead bool, so it says suspended computation, which when I run it will perform a read effect and return a value of type bool. And that expression is pure. At the moment it's just a value. When I run it, the value is bool, and then the type of that whole expression is now read, because I've activated that expression. By running the expression, I release the effects into the context. Now the overall value of that expression is really a Boolean. I can do a case match. But now this is an effectful expression which when I run it will produce a value of type color, and it also performs a read effect. And then finally the box keyword takes this effectful expression and then boxes it back up into a suspension. So now I have a value which is a suspended computation which will perform a read effect when I run it and return a value of type color. And the thing is pure again. So what is this run thing? Run is safe perform I/O. Okay? That's what run means. So unsafe perform I/O of type IOA to A is unsafe because when you apply it, the type system forgets about the fact that the expression had an I/O effect. That's why unsafe perform I/O is unsafe. With this system, we arrange that when you perform a run, you remember that the overall expression now has this effect. And then later on you can suspend it again and then remember that information. This is the key difference.
There are two runs. In which order do they? Two runs inside the box.
Left to right. So I do yeah, so it's left to right, top to bottom. So it has the syntactic order is the order which the effects happen in. So this is a default script language. It's not lazy.
Well, it's strict.
It's strict. So it's strict. So I have a explicit sequence or an implicit sequence in there. So this run and box thing is the reason I like this, and I'm talking about it at a Haskell Implementers workshop, is that this effect system is a clean extension to the pure lambda calculus. For example, so what we have, these are the standard rules for a simple lambda calculus. We have var, abs, and app. When I need to modify these rules to talk about my effect system, but when I add the effect tracking to these rules, we get the natural extension that we would want. So at the top, when I take the type of a variable, that's a pure computation. When I form a abstraction, that's a pure computation. And when I perform an application, the overall effect of that is the effect of computing the functional expression and the effect of computing the argument, and that's all. So it's like the effects happen separately to the pure computation. And these are the rules for run and box. So when I'm running a term m, if the type of the term is a suspension with some effect which returns a value t, when I run it, the overall type of that is t, and the overall effect is the effect of computing the suspension and the effect of running it joined together. And then likewise, if I have a term m which returns a value of type t and performs some effect when I evaluate it, when I box it up, I get a suspended computation. The computation is indexed with the effect, and then the overall thing is pure. So it's a clean extension to pure lambda calculus. I did my PhD on effects, and back then I thought latent effects were a good idea, where you have tau1 to tau2 and you write the effect annotation above the arrow. This is a terrible, terrible idea. I can say that with authority now. The reason is it breaks the notion of substitution. Like lambda just means substitution. And isn't that a wonderful thing? You have pure function arrows which are just functions. So with index computation types, we retain what lambda means, and then the effects system is just a plugin to what we already have. So index computation types are good. And I will note that these are not monads. So the system with run and box, I'm not using a monad because there's no return and bind. Like a monad is type constructor, return and bind with the 3 monad laws. I'm not using return and bind. The run and box are baked into the system. So I lied a bit about when I said automatically escaping monads. It's really automatically dealing with effects with these index computation types. So I introduced these 2 new keywords, run and box, which is almost as annoying as having to rewrite expressions to use do notation. But if you think about this a bit more, run and box are very easy to insert implicitly, and it's always obvious when you would want to do this. Because, so if I was to not have the run there, and I've just got a read ref, and I'm doing a case match on read ref, the type of this read ref is a suspension type, sReadA. I can never do a case match on a suspended computation because it's not algebraic data. Okay? So in a scrutiny of a case expression, if I have a suspended computation, it's always safe to run it, because otherwise I would have a type error. So during elaboration, doing type checking, I can insert that run cast. Okay? So now I've got that. It's also always safe to insert a box and just go from there to there. because this expression has an effect. It has an effect of performing a read effect, but I said before that we want our functions to always be pure expressions. So you add another rule to the elaborator, which says that if you have the body of a lambda abstraction, which has an effect, you just suspend it by inserting the box cast. So we automatically go from there back to there, okay?
Is that true even if you have a type that it can determine that it has to convert back into suspended?
Yes, because I said my function arrow just means function. So lambda abstraction does not suspend effects, which means that you do the type inference, and if the body of the function has an effect, you just insert a box, and then you automatically get the S-read color in the type in the result. So there's a few other cases. Say I have the usual type of add, say nat to nat to nat, and I'm reading a reference in both arguments. Well, read ref is a suspended computation, but then add it requires a nat, so I can safely run insert run casts. So this happens during elaboration. Now, the reason I can do this implicit inserting of casts is because I use bidirectional type inference. This type checking algorithm is based on Joshua Dunfield and Neil's complete and easy bidirectional type inference for higher ranked types, which he talked about a few years ago at ICFP, which I fell in love with. So in a bidirectional type system, you break the usual judgment form into two versions. If you know about this, you have a synthesis version and a checking version. So synthesis means that if I have a expression, I can always synthesize the type just from that expression. So given a variable name, I can just look up in the context to get the type of that variable. So the right arrow here means synthesis. I have another direction called checking. So I say, if I know that my expression is supposed to have some type tau1 to tau2, I can do type checking by adding to the context x, the parameter supposed to have type tau1, and then check the body against the body type tau2. For applications, if I have a term applied to another term, I can synthesize the type of the functional expression and then check that the argument has the same type as the parameter of the function. So we have this synthesis and checking modes. And then there's a rule which is the interface between synthesis and checking, which is what this says here. When I say synthesis and checking, that's the same as when GHC complains about inferred type does not match expected type. So inferred is synthesized, expected is checking. Okay? Same idea. So what this rule says, that if I want to check that term M has type tau2, but I infer or synthesize that term M has type tau1, that's okay, provided tau1 is a subtype of tau2. So I was checking that M is a vehicle, but I inferred that M is a car. That's okay, because car is a subtype of vehicle. When you're dealing with higher ranked types, you use this subtyping to deal with instantiation of type schemes. So if I want to check that this term has a type like int to int, but I infer that the term has type for all A to A, that's a subtype of int to int because I can instantiate that to get the type that I want. Okay? So use that same idea. This rule is a hook where I can hook implicit conversions and wonderful things. I say that in my system, if I'm trying to check that this term has type tau1, but I infer that the term is a suspended computation, which would return a value of type tau1 if I run it, when I just run it, I insert that run during elaboration. And so there's a couple other things you might want to do. So if you have a situation like this, where you have a foo function which takes its first argument and then performs an effect before returning a function which takes the next one, you can also, I'm sort of running out of time, so I might just quickly go through this. It's the case where you do another implicit thing during elaboration. So if you have a function application, in the functional expression, you're expecting something of type A to B or B to C in this case. It's never the case where you want a suspension there, because if there was a suspension there, then the type application or the application would not be well typed. So it's again also always safe to run that. So I might just skip over that one. So this system is implemented in DDC, and it does the elaboration which I've just talked about. For example, here's a DDC module. So I have this function 6, I have lambda x, and I'm doing a read ref. I'm reading the reference, and then here's the other example. I have a function using case alternatives. So 7 reads matches a color where the color is just a value, and I have this 7 ref version where the color is stored in a reference, and I'm doing a read ref in my pattern alternative syntax. So if you want to experiment with this, you can take a module like this, and you go to the command line and you say ddc load d.ds, and it gives you the core program, and you can see it's automatically inserted the boxes. So here it automatically runs the computation which does the read ref, and then so your boxes up effectful computations in the body of lambdas. So see box, and so on. You see this is our notation for explicit type application. Okay. Any questions? Yes?
Can you selectively remove one effect and keep some other?
Yes. So this here's some more examples. So I'm using this in where's another example? Here we are. So this is the core of my text library, which deals with flat strings, and in this I wrote a function which copies a text to a vector. So in this language, text objects are primitive things because literals are stored in the text segment, and I copy it to a vector. So with this type, this suspended computation, if I was to run it, would read some data from a region called R1 and then write to a region R2. So you can have more interesting effect expressions as well. Lena?
Are you stuck with some effects that you have decided, or is it extensible?
It's extensible. So I have read, write, and alloc, these standard memory effects baked into the system because it has a region system. So I can create new local regions with syntax in the core language. I've also got this region extension form. Where's an example of that? I can have an existing region, extend it with a new chunk, and assign more capabilities to that chunk, and then when that returns, the new extension joins the old region. So that stuff is baked in. But you can define your own like a console effects or reading writing to the file system. I do that in the base libraries. Another question?
Does this mix with continuations?
What do you mean by that?
Well, continuation monads, say, called CC.
No. So this, something I've learned recently about effects. I've been reading Andrei Flinsky's work on reification and reflection. I wish I had known about that a lot earlier. So if you read his work, he says that all effects ever can be implemented as combinations of state effects and continuation. So I have state effects, but I have not implemented continuations. That's something I'd like to do. So run and box is much like reify and reflect, and I can do this for state computations, but not for, I haven't implemented continuations. But yeah,
Have you explored the connections with modal logic?
this is a modal logic. This is exactly.
Yeah.
So I realized that this was the way to do it after reading Rowan's paper on judgmental reconstruction of modal logic, which also uses the words run and box. So the formulation is a little bit different. I wish I had been told about that a lot earlier as well.
It's also Frank's paper.
It's also Frank's paper, that's right. They're both really good papers. So judgmental reconstruction of modal logic and Andrei Felinsky's stuff is gold if you want to learn about effects. Yeah?
How does this differ from the bang syntax in Idris?
I have looked at that, but I haven't really sat down and used it. I think bang implies lifting into a higher monad stack. So in Idris and in Haskell, when you're using a monad, you're using an encoding of effects in terms of passing state parameters around. You can imagine that the approach to effects in Haskell is to encode the denotational semantics of effects by passing values around. Whereas in this system, you bake knowledge of effects into the type system as a primitive concept, which allows you to do other things, deal with capabilities and regions and whatnot. But at the same time, I only have state effects. I don't have parser effects and that stuff. Yep.
Just a clarification, bang in Idris is just a straight syntax rewriting thing, kind of like denotation. Okay, there's nothing fancy going on at all.
What about lazy languages?
So I had a, if you read my original thesis, I did have an effects system which worked with lazy languages, and there was a story about how you might do that. But that system used latent effects, which I later realized was a terrible mistake, because if you have a effect variable above every function arrow, when you want to start writing higher order functions like map, mold, and fold and filter, you end up wanting to be polymorphic on all possible effects in your higher order functions, and you have this explosion of degrees of polymorphism. It just gets too hard to manage. So I think this system, I've written several hundred lines of code in the base libraries to deal with basic data structures, and it seems to be quite usable, much more so than my original thesis. Okay? Go.
Is that because your polymorphism will handle effect type and non-effect type the same way? You can instantiate one or the other?
So this new system is bidirectional type inference, so it does rely on having type signatures in some places. So to tell it when it's expecting to have a suspended computation type. In my original system with latent effects, it was a constraint solving system, and I had problems with poisoning. If you know about, you do constraint solving, information flows both ways, and you end up with effect information being poisoned. If you want to know about that, then ask me. So, yep.
What do you use it?
Oh, it's on package. So if you search for my name, you'll find my website. But I did an update a few weeks ago. You do cabal install bdc-tools, you should install it.
Are there cases where you still need to manually box and run two effects at once in order to control?
So if you have a polymorphic list and you're putting ints in there, you might want to make a decision whether you want to put ints in the list or you want to have suspended computations which will return ints. So in that case, you'll either need to write a type signature or manually put run boxes in, but you can do either of those.
Okay, so let's thank Ben.